Um, this is the last of 8 classes on energy and economics. And what I want to do is review very, very quickly. I'm just going to fly through various summaries of the rest of the class. And what I want to talk about something that's bothered me a whole lot, scared the bejesus out of me, and about energy. And I want to open it up to questions. Now, this can only operate if we can go through my slides very quickly. But I would like you, if you have a question, this is a review of the course. If you have a question, I'd like you to raise your hand or write it down and we'll deal with it later. So here is what I consider to be the main points of this class.
Share screen.
Oh, share screen? I did push share screen. You can't see my screen?
No.
Oh, shit. Excuse me. Share screen. Okay. How about now?
It's yes.
Yes.
Okay. All right. Sometimes I have a problem when I put on the PowerPoint, but it looks like it's fine. Okay. So this is the 8th lecture. And we want to have a review and ideally a discussion. And we want to talk about the important things of this course that you may not get otherwise, is peak oil, energy return on investment, and limits to growth. And I was really, really made conscious of this by some comments that went to a nice dinner party last night, and some of the things that people said about energy were just smart people, were just amazing. Okay, so the objectives of the first lecture were to understand the earth around us, how important energy is, honor those who helped us understand, and then try to get the idea that energy is not just something that's in the physics lab, but that's part and parcel of absolutely everything that goes on, and especially part and parcel of our economy. And it's not taught that way. So that it's, unfortunately, usually energy is only taught in the physics lab or one chapter in ecology. But I gave you the example of whenever I'm washing the dishes, I'm thinking of Gibbs-free energy and emulsification energy and so forth and so on. Now, I think ancients understood the importance of energy because many, maybe most of their gods were one way or the other. Ra in Egypt, Zeus in Greece, Vulcan, Prometheus, who brought fire to humans. These were all about energy, and they were gods. Of course, they had lots of other gods too. The origin of our present understanding of energy starts with this guy, Sadi Carnot, a French military engineer. And he found out that it was not heat that was needed, but a gradient in heat between hot and cold, or in any energy situation, a gradient between more and less. And for example, a lifted weight versus a lower place the weight could drop to. You always have to have a gradient of force to allow energy to do its thing. Lots of what in our daily lives are chemical gradients. And then this guy, Joule, who was a brewer, figured out the relation between motive energy and heat. And see if I can, I think I can do this there. And so he drops a weight so many meters and looks at how much he has paddle wheels in this insulated container, and he looks at how much heat is generated from the physical work that's done. And then for the first time, we began to understand um, the relation between energy and heat, which had really confused people for a long time. And then Thomson, Clausius, I think that's Claudius, Helmholtz, and Lord Kelvin gave us the laws of thermodynamics. They're really critical importance in saying what they are very straightforwardly. The first law of thermodynamics is the quantity of energy is conserved. The second law of thermodynamics is the quality of energy is not conserved. So every time you have a transaction using energy, some of the energy is lost as heat that you can no longer use. Okay, then the second presentation, early Earth environment and the evolution of light, and we talked about ecology. So here is the importance of the sun. The fact that the sun, since the Big Bang, we think, has been using up its energy in fusing and making helium and generating low temperature energy unavailable for work and life. This is the machinery of life that intercepts some of the sunlight as it goes out into space. Most of it goes out to space and does essentially no work. Then something that happened that was really important was the evolution of green plants, which oxygenated the environment. And you can see in this rock from Glacier National Park that the origin of green plants is the line between the grayish green and the red rocks. They're made of the same materials, very heavy in iron, but the ones at the top are rusted because there was oxygen in the environment. And oxygen was originally a toxin, but allowed plants and animals to use energy much more fully. And then came all of this amazing stuff of biological evolution. And here we are at this little piece right here at the end and wondering what's going to come next. Now, occasionally, the whole evolutionary thing is reset with either very, very big volcanoes that push stuff way up in the stratosphere, or with meteors, big meteors coming in and causing terrific changes in life. How do you measure the energy flow in nature? These guys, Lindemann and my own doctoral advisor, Howard Odom, were the ones who basically figured out how to do it. And I gave some pictures of how we as a class, 30 people would go out to a stream and measure the flow of energy from the sun to the plants, to the insects in the streams, to the fish in the streams. And just amazing, just about a 10% efficiency at each one of those steps. Okay, the third lecture was about the evolution of mammals, proto-hominoids, meaning early human types, and our own species, the increased exploitation of energy by humans, and the evolution of agriculture. Now, hypothesis one is natural selection. Evolution by natural selection is what's caused the world to be as it is, and including what happens to us. And here are some of our ancestors, and you can see, or near ancestors, and you can see that our jaw has moved back. Our zygomatic arch has become less robust. Our brow ridges have become less until we have the modern face. And if we stay on this planet for another 100,000 or 200,000 years, we might look quite differently in the future. Who knows? Now, this is indicating that energy also was important to our ancestors, and that a spear was an energy concentrating device or a force concentrating device, a spear or a knife blade that allowed humans to exploit far more mammals, because it's tough to get your fist through a skin, and fire, which allowed us to exploit far more plants, because plants basically have cell walls and they're hard to digest. Here are some people who are hunter-gatherers, much as we think our ancestors were, the Kung in Botswana, and they Is that a question?
Hi.
And they can carry all their possessions
Yeah.
on their backs when they move from water hole to water hole.
Listening to a course.
Oh, I've got two primary.
What's happening?
We've got one person who's not muted. It's Rob. Oh, looks like he just fixed it.
Okay, thank you, Marianne.
Mhm.
Okay, how are we doing? We doing okay? So humans came out of Africa, maybe 100,000 years ago. It's thought a lot of evidence that humans evolved in East Africa here. And the people in Africa that are in South Africa or in West Africa are just as far removed as from the people that were in East Africa 100,000 years ago, as are those who moved to Asia or down into the Americas or into Europe. So all of our ancestors moved greatly over the whole earth, and yet we find that ourselves as a species are genetically almost identical. It may seem that humans, different groups of humans may have different appearances to one another, but in fact, we are genetically, I think only a cheetah has less genetic variation than humans. Then the next most important thing with the evolution of humans and energy was the evolution of agriculture, moving 10,000 years ago from hunter-gatherer to agriculturalist, staying in one place, sometimes accumulating a surplus, and doing some amazing things that help us today. So that maize started looking like this on the left and was genetically engineered long before we were using the term in the modern context. But over 10,000 years, people just saved the biggest seeds, and here's what we have is the corn or maize that we have now. Lecture 4, the Industrial Revolution, the importance of steam, coal, making steam, running these gigantic energy materials, and James Watt steam engine being especially important, and leading to Jevons paradox that as we made our engines more efficient, people found more uses for them. And although we might have been trying to save coal with our original engines, by making them more efficient, we actually ended up burning more coal. And that's happening today with petroleum and other things. Along came the Industrial Revolution with straps made from buffalo hides in very dangerous conditions. I mean, it just gives me the willies looking at those gears going round and round, and a woman with this long flowing dress, and some terrible, terrible accidents occurred, ultimately leading to workman's compensation. William Stanley Jevons was very important in understanding the importance of fossil energy, of coal in England, and his Coal Question, published in 1860 or so, is it's today a fantastic read. On the 5th lecture, I talk about peak oil, energy return on investment, and limits to growth, that we've had this tremendous increase in wealth due to our increase in use of fossil fuels, and principally due to that. And how should we think about it? And this fella, M. King Hubbert, who I knew, was probably most important in getting us to understand the relation of energy and its use over time. And he came up with this idea of a Hubbert curve, that over time, the use of a non-renewable resources such as oil would initially increase more or less exponentially as people figured out more uses for it, would reach a peak. And when roughly half of the resource had been exploited, and then would go down the other side. And it's really hard for people to see that because things are still growing just before the peak, when things are likely to change a whole lot. I've done a lot of work on oil, and the red line is the official statistics of our oil reserves, which are a fairy tale, are wistful thinking. Our actual reserves of oil are in the green line, and how you get this figured out, we put out in our scientific papers. We try to say carefully how we do it, what our assumptions are, and we try to examine our assumptions versus the actual data. And we're pretty good at it. And this is 3 estimates of our use of all fossil fuels. This is a low estimate. This is maybe a best estimate. And this is the most they can imagine, the people who did this, who were from Australia, of all fossil fuels, extra heavy oil, subbituminous coal, every kind of resource you have. And you've got to realize that whichever estimate you have, and it looks like the lower estimate is the best one, we're going to reach a peak in use of all fossil fuels. And in fact, I think we have. Just about now. And one thing is clear to me, we made a mistake earlier because we didn't see shale oil, but shale oil came along. It really helped the United States, and I'll show you some diagrams to that effect. Now, the idea of there might be limits to growth was not part of our whole social milieu, and the first guy to think about this was Jay Forster, and this was a very famous book in 1972, and that book is still, the predictions in that book are still pretty good, very good. And so I think depletion of our high-grade fossil fuels is likely to be a much bigger problem than even CO2 and warming effects. Hard to say, but I think we should be concerned about. We made these models, myself and my students, about the economy requiring energy to make GDP, which you can either invest or put into consumption. That's what we like. Go to the movies, buy a car, whatever. And you see here in 2007, the amount we had to put into getting energy was small, but as we deplete the best energy resources, we assume, and we have good evidence for that we have to put more and more energy into getting energy. And are we going to reach this situation where, as in England in 1400, half or more of the whole economy is just getting the energy needed to run the economy, instead of 5 or 10% today? This is our hierarchy of energy needs. We first need to get energy to extract energy, because we need the energy, then use it to refine it, and then take it to where we go. And then the most important thing is grow food. And this is basically grow or capture food. And this is basically what most humans that have ever lived are somewhere down here, except for a very, very few. But if we have more energy surplus, a higher energy return on investment, then we can have education, healthcare, arts. Lecture 6 is a review of conventional economics, mercantilists, physiocrats, classical economists, neoclassical economics. And I made the point that even though they are viewed very differently from economists, they were all focusing on the main energies, economic energies of their time. Mercantilists on wind, physiocrats on land, intercepting solar energy, classical economists on labor, and neoclassical economists on the capital equipment that allowed the use of fossil fuels. It's important to, I hope you go away to realize that what we consider economics today is only one of a variety of ways that past economists have thought about economics, and that some economists today, if I want to label myself for the moment an economist, think about it today. It's almost an accident we think about economics as we do. Here's some early economists, Malthus, who said that the population would grow exponentially and the resources could only grow linearly. Adam Smith was a classical economist and wrote The Wealth of Nations. And Karl Marx, who thought a whole lot about capitalism and just a little bit about communism and was very thoughtful. And then the birth of neoclassical economics in 1880 that happened by the resolving of the diamond versus water paradox. And they would get what my an economist friend of mine said, I said, what'd you learn in your undergraduate economics course? And he crossed his fingers like this. In other words, the relation between the theoretical relation between supply and demand as expressed in markets. Keynes was very important, government intervention, and why we need biophysical economics. Here's a good way to understand the importance of fossil energy in today's society. Mostly people don't think about it very much, but this is a 33 horsepower, 33 horses here, harvester. And takes 5 people to run it and lots of stable boys and lots of leather and all kinds of things. And here's a 200 horsepower harvester today that just takes 1 person to run it. Also, of course, some people to get the oil out of the ground. And this is the view of contemporary economics. Economics is just about the flow of goods and services and land, labor, and capital between households and firms. And this is my view of the minimum diagram by which we can describe an actual economic system, which is based on the natural sciences and on the need of energy at every junction and the flow of materials from nature to the final consumption. And contemporary economics basically looks only at this last column over here. We have a book on this. It's all kinds of details. And I'm going to make good. I'm almost done, and we can open it up for questions. I'm looking at a couple of recent things that happened to me this week that got me quite concerned. This is the so-called proved oil reserves in the United States. And just to give you an idea, we're using, we have somewhere around 48, but we're using, depending how you cut the pie, between 3 and 7 per year. So it's a little bit nervous. And this is tight oil or fracked oil, which has made a terrific difference, both in production and consumption. Now that's how we look at the resources of oil, but let's look at the resources of the United States versus other countries. Here we are, way down here, about the same as Libya or Nigeria. And China less than us, Brazil less, and so forth. And then Russia has about twice what we have, at least. And then in the Middle East, United Arab Emirates and Kuwait and Iraq, and let's forget Canada for the moment, and Iran and Saudi Arabia. So, I mean, just take Iran, which we have been on prickly relations with, and the US they have 4 times more oil than we do. So if you think that the strength and the wealth of the United States, its ability to win World War II and whatever, is dependent upon oil, which it is, we may not be the big player coming into the future. And another thing I just found out this week that I don't have ready good pictures of is that of the oil that we burn, about a third of it comes from natural gas wells. It isn't even oil. I was very confused as to why we produced 13 million barrels of oil a day but consume 20. And the difference is butane, propane, hexane, natural gas liquids that come out of gas wells. And the gas Hubbard cycle is after the oil one, will take place after. Now, I was at a party last night and I said, well, about 2/3 of our energy comes from petroleum and about 80% from fossil fuel. And all kinds of people said, you're crazy. That oil and gas are only 40% of the energy that we use. So this is the most recent official data, April 2023. And you see that renewable is the biggest chunk well, almost biggest chunk is hydroelectric, is dams. Here's solar. Here's wind. Now the renewable are a big part of electricity, but they're not a big part of our total energy use. So when I was in this conversation last night, people were just blown away. They had no clue. They thought we were running mostly on solar, on wind turbines or something. So, okay, I am done talking, and I am hoping that there are going to be people that are going to ask me any questions that you want.
I do
Yes.
have a question. Oops. Go
Yeah,
ahead.
Yes.
My question is to do with water, if that's okay. In
Yeah,
terms
sure.
of, in terms of
Who's
depletion.
this, Rob?
Yes.
Okay.
I've never understood I don't ever understanding of the depletion of water. It's stated that we run out of water. It's my understanding that there's the same amount of water on the planet that has always been on the planet because of the water cycle. Can you explain that to me?
Yeah, good question. And I'm just trying to get back to where it was here. Water obviously has its own cycle and it's constantly renewed. And so water, you might think, well, as you say, the amount of water on the planet of the Earth is sort of constant, pretty close to constant. A few molecules escape to space, and I think I understand that that in so many billion years, the molecules on Earth of water, like in the past for Mars, will go off into space. But that's trivial. What we do is we deplete usable water. And the most important water that we deplete is groundwater. So all through, most importantly in the United States, all through the Middle West or to slightly west, from Texas up to Colorado, there's this huge Oglala aquifer, and the water is fossil water. It's often hundreds of millions of years old that got trapped between sand grains down there. So the most important aspect of depletion of water is, one, pollution, and I think you understand that. And two is that when you pump the groundwater out, it's been down there for millions of years. The rain is not reaching down there. And even if it is, the sand grains, when you take the water out, because they were laid down with water originally, tend to compact. So it then can hold much less water. And that's what's happening. And how the farmers see it is that the cost of getting water increases every year because they have to pump it from deeper each year as they deplete the cell, as they deplete the reservoir. The level of the water goes down, 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 down. So it costs more energy to pump it up, even though there's water down there, until you use it all up. And I don't know what you're do at that point.
Yeah, but I'm confused again, because now you're saying we've used it all up. So I thought there was the same
No,
amount.
we've used a lot of it up. I'd
But you-
say, let me just say half. We've used up half the water from the Oglala aquifer.
Well, where did it go?
It might be better to say that we've moved all the water
Yes, we moved it
from
into
the
the atmosphere.
reservoir up. So
We
it
moved it into
hasn't,
the atmosphere and into the ocean. How's that?
so it's
Okay.
no longer in the ground. So it's not transformed into something other than water. But
Right,
what is
and it's very
depleted is that
hard.
reservoir.
It's very hard for us to pull it out of the atmosphere because that happens when it rains.
So what happens when it rains? Doesn't the water go back into the ground, or when the snow melts?
Well, it won't go down into the groundwater reservoirs because they were charged over millions of years, and they won't recharge in tens of years.
Thank
In other
you.
words, it's millions of years, even billions of years of rain that was captured in the groundwater aquifers.
Another
And
way
so-
of saying it is we're pulling it out of the ground at a faster rate than it is being replenished by the rainfall.
Yes,
Do you get that, Rob?
Yeah, I do. It's a good way to describe it. Thank you.
yeah, good for you. I mean, this is good to have any of you say it better than I can, which seems to sometimes be the case. Okay, did somebody else have a Elaine?
Yeah, me. Some years ago in studying some of these topics, we were told that the oil coming from Venezuela is of a lesser quality than oil from some other places. Can you address that? Is that true?
Yes, so this diagram I showed you, the largest, can you see my screen?
Yes.
The largest reservoir of oil in the world is in Venezuela, but it's not like oil that we run our cars on and so forth. It's called tar sands or extra heavy oil. And there's a lot of that, and it's not clear. Canada and Venezuela have most of that stuff that's in the world. And Canada is exploiting some, and Venezuela is not exploiting very much. For one thing, it's like trying to get oil out of your street. That stuff that we tar our streets with is long chain, heavy petroleum, long molecules of petroleum. And it's petroleum, just like it's rock oil. But what we do is when we refine oil, we take the sludge, shall I say, left at the bottom of the refining purpose. We take the next to worst stuff and put it in ships. It's called bunker. And that's very polluting, heavy, nasty oil, lots of sulfur. And so they burn it in ships where people pay less attention to it, although they're starting to. And then they take what's called the bottom of the barrel, and that's sort of where this term comes from, the stuff that is least useful economically, and we tar our streets with it. Now, the problem with the Venezuelan oil is it's all bottom of the barrel stuff. It's all basically, I mean, it's real good for tarring streets, but here's how you take heavy oil, long molecular chain oil, and turn it into gasoline or diesel or something you could use in your car. Is you crack it. And you may have heard about cracking towers that you pass in California or New Jersey or down in Louisiana, where they take oil and they crack it, and it comes from cracking the whip, because basically they get the molecules really moving with heat and get them flopping around, and they crack, they break. And the best hydrocarbons are usually considered those that are 8 carbons long, octane. That's why when you go buy gasoline, it has an octane rating. And if it's 97, then it has properties of use that are 97% as good as pure octane, just 8 carbon length gasoline. Well, hardly anybody gets that, but racing cars maybe. And so these cracking towers take the oil out of the ground, and some of it's heavy, and some of it, like fracked oil, is relatively light. And just with amazing chemical engineering, they turn them into useful lengths, ideally of 8. But some of them come out as 1, and that's methane, and 2 ethane, and 3 propane. So you put all this stuff into their big refineries and turn the valves right, and you get these things we can use out of the refineries. We can't use them without that chemical process of getting the carbon chains into the right length.
So is the Venezuelan oil longer chains and takes more processing?
It's thousands, even hundreds of thousands of carbon lengths long.
Hmm.
And I might be wrong here, but I think the reason is that it's undercooked. When you cook oil at the right temperature, about 100 C, for the right time, about 100 million years, you'll do the cracking in nature. And you get good stuff coming out right away. And then what petroleum engineers learned to do over time was take petroleum molecules that were too long or too short and combine them or split them and get into getting something useful. Now, if we took you, Elaine, and put you into a refinery, the refinery would balk a little bit because your life has pretty long chains of carbon. And what happens is that life usually has hundreds or thousands or tens of thousands of length carbon chains. That's what you're made of. And so ideally, life, which was where oil started, that's why if it's properly cooked or pressure cooked, we say, for 100 million years, then you take this yucky stuff that life is made of and split it into refined materials that are like gasoline or diesel or something. Okay.
Thanks.
I've got a question
Good.
for you,
Yeah.
Charles. When I look at those Hubbard curves,
Yeah.
they go out to like 2200, and so I'm not sure where the peak was, but there's still a lot of oil out there.
Yeah.
We won't use it all. Well, we'll get a little bit past the peak when I can't see now. The curve is too small, but it looks like around
Well, that
2200.
would be roughly 2025. Yeah.
Well, no, I
now we
see.
don't know how much for sure. There
Yeah.
is, so this one has 20, maybe just a little 2045, and this one 2075. So
Yeah.
we don't, but the point is, and I just been looking at our rate of gas use in the United States is just climbing so fast. And I think people are going to be, our estimates of how much gas is left are that we'll reach a peak in gas in a year or two because we're using it so fast.
Well, you're speaking of peak of gas in terms of US resources, right?
In this case, yes.
But I mean, we're talking about global resources. What I'm saying is there's a lot of there's a lot of those carbon chains in the ground. Now it's carbon that when you burn it goes into the atmosphere as CO2. And my
Correct.
question is, you got all this carbon in the ground and we're extracting it and burning it and we're taking it out of the ground. It took hundreds of millions of years to get it there. And now in a matter of decades, we're
Yep.
reversing that process
Yep.
and putting it back in the atmosphere. The question I have is which is going to come first? The clear evidence of climate change in terms of temperature surge or running out of petroleum? Which do you think is going to come first?
Well, I've just recently written a paper on this with my colleagues, John Day and others. And we say it'll be a perfect storm in the coastal zone because over the next 50 years, the ocean is rising. That's due to thermal expansion when the ocean gets warmer and glaciers melting and ice caps melting. So the ocean is rising. Everybody wants to live along the edge of water. So the housing goes in there full time. Climate change appears to be happening, and let's just say it produces stronger hurricanes. That's some people certainly think that. And so, how have we adjusted to former storms, severe storms, and sea level rise and so forth? Well, we produce a lot of dikes and seawalls and all kinds of stuff like that, all of which requires energy. So just when we're going to be needing more energy to repair the things that are going wrong climatically, then we're going to, we think, be faced with a real sharp drop off in the amount of energy available to do the job.
Are these graphs this US, Charles, or is this worldwide?
These are for the world.
Yeah, okay, thank you.
The US might be, I don't know, 5 to 10% of them.
Well, just to challenge that a little bit, there are some who say the climate change is going to become a real problem in the next several decades.
I think the depletion of oil in gas will be a real big problem in the next 2 decades.
You do. Two
Yeah.
decades? 2 decades.
Well, here the best guy I know for doing this, his name is Jean Larrey. He's a Frenchman. Now this is tricky because I'm going to try to get this on my screen, and as I said, it's tricky. And I had Larrey's I had his email opened up. Let's see. Let me do a search here. I thought I had it open, but Laherr, John. Okay, I'm working with him on this paper on natural gas for the United States.
Share a screen too.
He's doing most of the work and I'm editing. But I'm a good editor. That's maybe my best job. Okay, so look at and any of this anybody wants, email me chall@esf.edu and I'll send it to you. Now, if you look at gas, gross withdrawal, and this is, see the last 20 years right here. This is how much gas we have produced in the United States, and it looks really good. Our economy is really humming along, and boy, oh boy, we can get lots more gas. Now, the trick is this green is fracked gas. Okay, you follow me? It's, in other words, we use the process of fracking, which I explained at one point, to break up the ground underneath, and it's been really good at getting gas. But if you subtract the fracked gas from the total gas, then what's left is called conventional gas, and that's the purple. This is all the gas we thought we had in 2007. And you can see that if we were dependent only upon conventional gas and not on the fracked gas, we would be in very bad straits right now.
By sharing
Because-
screen.
Oh, I'm not, sorry. It says I am screen sharing.
Yes, I see it. I see it.
We can
You-
see
you
it,
are.
but we could see it better if you maximize the screen.
I couldn't see it at all.
Maximize the screen. Oh, I don't know where to do that. Yeah, wait a minute, let's try this.
Oh no.
Yeah,
Hope
That's
I
okay.
don't
That's
block.
okay. We can see
Yeah.
it pretty well.
Here we
It's
are.
good
Can
enough.
you see this okay?
Yeah, it's fine.
So this is really telling you what's going on. Conventional gas and oil looks about like this. It's going down the toilet. Production is declining every year. Now, natural gas liquids, remember I told you this, I just figured this out this week. The liquids from this total natural gas provides a third of the oil that runs our cars and trucks. Amazing. Now, here is, oh, that's total marketed. Here's conventional gas, same thing we saw up there in the purple line. If we were dependent upon conventional gas, we'd be out of luck. And here's a lot of different, these are from the different fields, gas fields. Marcellus is the big one, that's in Pennsylvania. Permian in Texas is a big one, but you see they're all peaking.
Yeah,
They're all
but I guess my question is, this
Yeah.
is valuable. I don't dispute that, but you're looking at the rate of depletion or of a region which you've already described is a relatively small region in terms of oil and gas reserves, right? We're a second tier, we're a second tier region. Now, when you look at the remaining reserves in the first tier regions like Saudi Arabia, and you look at the what we would do if we burned everything in Saudi Arabia, then we'd move on to Venezuela. There's so much carbon in Venezuela that
Yeah,
could
but
keep
it's
us
not clear
going.
we can turn that stuff into fuel. That's the problem.
Well, we could
Because
crack it.
we
It would
talked
be a little bit,
previously-
it'll be a little bit more expensive, but we would crack it and use it for gasoline. It would be a matter of cost, but the resource is there. I'm just saying, I'm worried that there is just too much of this stuff in the ground, tempting us to use it, burn it because it's there, and not because we're taking the climate issue seriously enough.
I don't disagree with you. I don't know which one is of greatest concern.
Yeah. I mean,
So
I think they're
you
both
might
of
be,
concern. But
I
the
was
big
gonna
question is
and
which wall do we crash into first? The climate wall or the resource, the economic resource availability wall? We're going to run into a wall one way or another. But
yep, limits the growth.
one wall will affect our grandchildren. Another wall may affect our great, 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 great grandchildren. I would just like to.
I think they'll both affect our grandchildren and possibly children. Now,
you
I
th-
just want
okay.
to answer a question you had before.
Yeah,
Because you said the world compared to the US. So this is for the world.
yeah.
Okay, we published this a year ago. How much oil remains for the world to produce? And so if you want to get in there and see how we do it, you know, one thing is you got to look at all the categories of oil. And these are the official pronouncement, which I told you are almost certainly, well, they're clearly wrong. Here's the actual finding of oil, the green line, and here's 1980, right about here, and here's our use of oil. So you see, we're only finding a tiny amount of oil compared to what we're using these days. And yeah, I'm happy to send anybody how you do this, and this is a process. The best way we know to predict how much is remaining. And here are the graphs that we get for conventional oil. It's the purple. That's just what's called conventional oil. You get out of the oil well out of the ground. Now, for the estimate of the fracked oil, which is very important for the US, but is not important for the world, is the difference between the purple and the blue. And incidentally, these are our projections of how much there are. And then if you add in the Venezuelan heavy stuff, you get the green line. So the Venezuelan, see, the largest amount of, by our estimates, and I think they're good, by our estimates, the largest amount of oil is conventional oil. Then we have the difference between the blue, the purple and the blue, that's fracked. And this is extra heavy from Venezuela and Canada. And the thing that's really interesting, if we burn natural gas liquids, that's a lot more. So we need to understand natural gas a lot more. That's why we're doing this new study. Can you follow this graph okay?
Yeah.
Mhm.
Okay, now look, when are your grandchildren going to die? Somebody give me a time.
Oh, gosh, 100 years? Just for the
100
sake
years
of,
from now, well, 2100. Well, look what we're going to have for the world. We're going to have maybe 20% or 100% more people. And we're going to have, even at the most generous estimates of how much petroleum, liquid petroleum you're going to have, it's only going to be half of what roughly that we have now. That's what we think. And the good stuff is the purple line, because you can make motor fuel from that very readily. The best stuff is going to be much less available. And the thing is, people will have no clue what's going on. They'll be like the people I talked to at the party last night. Oh, you know, oil's only 40% of our energy use.
Well,
Okay.
so this should encourage us to move faster to renewables. Unfortunately, the oil companies only look a few years ahead, and they're looking at their bottom line.
We're trying to calculate how much oil you need to build this brave new world of renewables. It's a lot.
Mhm.
And what you've got to do is you got to divert it from consumption into investment into this new world of solar panels and wind turbines and whatever. And it takes a lot of materials. So it's not going to be easy. Can we do it? I think we can do it, but it's not going to be easy at all. And I think people have to be realized that what you're going to have to do, here's what's going to happen. We're going to have to divert more of our output of our economy to getting the energy to run the economy. And that means more, as the energy return on investment declines, energy itself is going to become more more expensive. And since everybody, energy is used to make everything, people are going to see this mostly as inflation. And what happens when people see inflation is they blame their leaders. How's that? So I think that's much of what's going to happen is something like that. So I worry about the continuation of Jeffersonian democracy when people blame their leaders for every little bit of inflation, which is inevitable as we use up our best resources. So that's my commentary on political science, that the resources ultimately are going to be running the political future of our country and other countries. What do you think?
Well, one implication of at least on the fossil fuels resource availability side of things is after we get over this temporary period of extraction of cheap, tight oil, then we're going to go back to being highly dependent on the Middle East and other far-flung countries for our oil supply, which means suddenly the United States is going to be competing again with other countries for limited oil. And that's going to make the Middle East another field of global geopolitical competition and probably warfare. So it's like, I mean, we need to be using this period of temporary energy self-sufficiency to prepare for future scarcity, or we're going to have a very violent world. We're one of the biggest consumers of oil in the world, and what you're saying is we're operating under this illusion that fracking is going to go on and go on and go on, and we're not preparing at least for the possibility that that won't, it seems to me. And you know, here, so one implication is we've completely alienated the Arab world just in the last 6 months. And that's partly because I think we can afford to, because we don't depend on those countries for oil anymore.
We used to think
so
we did.
We can say, up yours, Saudi Arabia, up yours, Iran. We don't need your oil anymore.
But I think there are people who understand these things in our military and in our government. I think they understand these things very well. They don't talk about it because nobody likes to hear it. But I think that, you know, the United States is still working behind the scenes to make a joint political connection with Saudi Arabia. Saudi Arabia is afraid. They're afraid of Shiites versus Sunni Muslims and all of that stuff. And so they want the technology and the military technology of the United States. And I mean, it's a little bit terrible to think about all of these things, because ultimately it's about global power politics. And I don't know how long we'll be in a particularly good position. But if we make, there are some people in our country who, despite some issues, are trying to make a connection with Saudi Arabia, because Saudi Arabia is not particularly friendly with Iran. And they are worried about the power play. I think an awful lot of this is power plays. It's like Metternich is in the balance of power. I think over time, different countries align themselves with each other to try to keep one country from being overwhelmingly dominant, because that's not good for anybody. A little bit like, the Europe back in, I don't know, 1650 or something.
So Venezuela has the biggest supplies of oil, but it's not high quality. The next countries in that graph you showed that also have a lot of oil left, what's the quality level and how easy is it to extract that oil?
Venezuela and Canada have a lot of low quality oil, but Canada is producing it, and it's has a low energy return on investment. I'm on the committee of a guy at McGill University who's studying that for his PhD. So I'm kind of up on it, and its ROI is about 4-to-1, but they'll do it. And like some of you have said, I think we'll do it if we have to, because oil is such good stuff. From the perspective of people who are trying to run an economy. And that doesn't argue particularly well for the future of the climate.
Yeah.
And we had a fella that I was on here a little bit earlier, and now he's left. He was just visiting for a bit, Tim McWhirter, and he's a philosopher in the University of Maryland system. And we wrote a paper together. It's on what's called maximum power, whether there is selection for power, both in the natural world and in the political world. And all of these things I will make available to you if you ask me by email, chall@esf.edu, or figure out how to find me any other way, but I'd be happy to do that.
Charles, I have a question going back to Canada. Recently, FERC approved the extension of a natural gas pipeline coming down through Oregon and into Northern California. What's that about? Why does Canada want that down here?
It's all gas.
Money.
All right, the straightforward answer, yes.
Well, that seems to incentivize a lot of people. Not me particularly, but I've got enough, so I don't worry about it. Not Eric, but awful lot of people are incentivized by money. And how do you do it? Is you develop some resource and you sell it.
Canada also has a lot of hydro, which comes down south to meet the needs of California and the Pacific Northwest. And they've got a lot of gas. And I think Alberta has quite a bit of conventional oil as well. I'm not absolutely sure.
Canadian conventional oil is gone down.
Oh,
Production
okay.
is declining rapidly.
Okay.
Conventional oil. But the other stuff, they make up for it.
So, Charles, how do you compare? I don't recall you putting up a slide, but maybe you did, comparing the energy return on investment for different types of energy, like renewable, like wind and solar, and these other in comparison to fossil fuel ROI.
Well, I'm laughing because I'm in the middle of turmoil with people about exactly what should be the right numbers.
Oh, okay. Okay.
No, but I'm going to answer you. The solar people think their EROIs are very high.
Oh, uh-huh.
But I think that the methodologies that they use greatly underestimate how much energy is used to make them.
Uh-huh, uh-huh. Mhm.
So I'm going to show you something here. Just a minute. Over here, I've got 15 or 20 books in the middle shelf there that I've written about energy. So
Oh my gosh.
come over here and browse them or borrow them or whatever. So I'm going to get my one on solar. So I'm also an editor of a series of books for Springer. Springer's a very good publisher. And this is done with my friend Pedro Prieto. And the energy return on investment. And so you can get this for, I think, $55 as a soft cover and 45 for a digital or whatever from Springer. Prieto and Hall, you can look it up. And what we did in this is he was in charge of building a 1 gigawatt 1 gigawatt solar system in Spain, solar electricity system. He was the chief engineer. And as such, he signed, now, first of all, you see here in Spain, where the hell? Pardon me, in Spain is a real sunny place compared to every place else except Africa. You see?
Yeah,
So it's a good place to build a solar thing.
yeah.
Well, Pedro, as being the chief engineer, signed, sort of financial more than engineer, signed every piece of paper that for money, every bill that was for the project. And he came to me at a meeting in Ireland and said to me, looked me up and bought me a beer and said, I think that the people who are estimating the solar are really underestimating the cost, because I know the dollar cost is much, much more than just for the panels and for the inverters. She said, will you work with me to figure out the energy cost of my project? So I said, sure. And so we went through, just massive amounts of details of calculations of the energy cost. Well, basically what we did was we followed every dollar and assumed that when a dollar was spent, there was some energy cost associated with it. Less for business services, more for hauling gravel and whatever. And so we tried to do as much of this as possible using physical units. In that case, how much gravel, how many kilometers, how many meters, and so forth. But somebody's squeaking. And so we followed every dollar, and I have recently looked at the people that are used something called LCA, life cycle assessment. They follow only about a half or a third of the dollars. So I'm quite convinced that their estimates for solar, which are 10 to 20 to 1, are too high, maybe by a factor of 2. And when we were all done doing this, we found out that there was only about 2.7 thermal calories, heat calories, of energy return per calorie invested in getting the bloody thing to work. And we had to follow all kinds of, if you had to fly in the technician from Finland, because he's the only one in the world who figured out how to use this inverter, and it broke. All of those things we calculated for building a solar project in, we come up with, and I'm arguing with some good people now. I'm arguing with them that I think that their estimates are too low of energy return on investment. I'm sorry, are too high compared to others. But let me give you something. Oil now is between about 10 to 1 for a lot of oil wells in the US, maybe as high as 18 to 1 for fracking. And for good oil wells in Russia and in the Middle East, it's about 25 to 35 to 1. All right. And so natural gas alone is probably higher. Hydropower, it just all over the map because it depends completely on the site. Geothermal, not very good, 5 to 1 maybe. What else have we got? Nuclear, big mystery. Let's just say 15 to 1. That's the last value I can
And you
trust.
said solar was 10 to 1? Or maybe 5 to 1 if you're more
It
conservative.
depends where you do it.
Right.
There are some people who say north of the Alps, you can't make any energy profit at all.
What about wind? What is the
Pretty
EROI
good,
on wind?
18 to 1. Good
18 to 1.
studies by Elise DuPont. She's done good work on wind, 18 to 1. But that doesn't include intermittency, dealing with intermittency.
Right.
What have we missed?
Fusion.
So, they say they break even. They got this little thing about this big,
Yeah, right.
and they have break even. So I got the calculation somewhere. I figured out the energy cost of all of the lasers, of the electricity to run the lasers to get that little positive net energy. And it became, 1 back for 10,000 or something. And then I put in calculations of building the whole big tokamak and the whole big facility, and it was like 1 out of a 10 million return. So I don't know. I'm not holding my breath on that one, but who knows? Who knows?
Well, one of the difficulties of making that calculation is the numerator. The denominator, which is the cost, is a little bit easier to calculate, but the numerator depends on the assumption of how many years will this solar panel keep producing electricity.
Well, I would say the numerator is much easier to get than the
Oh, really?
denominator. Yeah, because there's all kinds of business. Should you charge for the business services? The energy cost, well, there's brick and mortar and lights on and computers and everything to run business services. And the real sticker is if you start including the energy required to give meaning to the paychecks, then it's really, really high. So there are some people who say, everything's so heavily subsidized with oil and gas, including my solar panels on my roof, because they're subsidized by the state of Oregon. So that subsidy is out of the oil and gas. I don't think I'm going to live long enough to get my money back from my 31 solar panels I put on the roof. But who knows? Just turned 81.
But someone after you may be able to take advantage of
Oh, yeah.
your investment.
But I got a picture, if you want to really get depressed, I got a picture down in Texas of square miles of solar panels that were all destroyed in a hailstorm.
Yeah.
I don't know if
Well,
anybody
that's-
calculated.
you know,
calculates that
the
in.
numerator is gonna be strongly dependent on the useful life, let's say, of the solar panel or the wind farm. And
You know, why
so,
not keep it on your roof for 50 years? It'll produce something.
yeah, right, I know. And so you've also got the uncertainty of how quickly the output will degrade over time. And, you know, we're just finding this stuff out
1% a
about,
year. No, I got numbers on that. 1% a year about.
oh, okay. All right.
Um,
Uh,
so here's what I think we need to do. You know, I'm a pretty happy, optimistic kid, and somebody said, you know this, how can you be so happy? Well, that's how I'm just basically a happy kid. And I have no children, in part to avoid this issue. I mean, I figured it out back in when I was 23 years old. So here's the most important thing is we need to educate people. We should have this course taught in Southern Oregon University, at every university in the United States. People to understand the pervasiveness of energy, how energy is generated or wealth, and how it's not going to likely be there, at least in the forms that we are used to, and that are very high energy return, that allow us to have a very wealthy society. So I think that's the first thing. Most of the green stuff that I see in the media, and it's all over the media, doesn't particularly thrill me, because I am pretty cynical at following out. You know, somebody had a high energy return on investment vegetable garden until I found out that they were importing chicken manure from Vermont into central New York State. And when you calculated that, the whole thing went down the toilet. So I mean, the energy return on investment got very bad, very fast. So you have to really do your homework here. And we haven't trained very many people to do the homework. So I don't know. I think we'll just sail into this, and whatever happens, happens.
you know, Charles, there's a way of using this methodology to compare an internal combustion engine and a all electric vehicle, to compare how much energy is produced by all of the well, it takes energy to make an internal combustion engine. It takes energy to make a battery, right?
Yep,
A set
we
of
are
batteries.
actually doing that. An institute that I'm part of is actually doing that. And the basic results are that after you run your car for 20,000 miles, they break even.
Okay,
Initially the electric vehicle takes more energy, but
right.
you get but it's not a big solve. It's not a big difference between a Prius, say, and a electric vehicle. And the electric vehicle uses 3 times more copper. Where are we going to get that copper?
So you're saying the crossover where the electric vehicle is starting to generate more, deliver more effective energy output than the
Over
internal
the
combustion
investment.
engine is about 20,000
Yeah,
miles, did
yeah,
you say? 20,000
yeah,
miles. So that
yes,
could be at let's say the average use of, well, that would be less than 2 years of
yeah.
driving.
Oh yeah, they're better.
Okay, so the electric, because I've heard this by, you know, critics of electric vehicles. Oh, how many tons of rock you got to crush to get all of the, lithium and the cobalt and all, and there's a lot of dispute around that. And so this is a very helpful uh, 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 thing to keep in mind, that after the second year, it's all gravy as far as the energy cost of the vehicle itself.
Well, it depends. In Oregon, we get a third or a half of our energy from coal and fossil fuel. So you have a lot of coal pollutants, which are worse than gasoline pollutants in the air by charging your car in Oregon. It's a little more complicated.
Well, I'm gonna push back on that because there's only the Centralia plant in Washington, and I think the plant in Oregon is going to be shut down soon. And we don't
We
import
can
any
deplete our gas faster.
what's that?
So we can deplete our gas faster.
Uh, well, I think PG&E, PGE and Pacific Corp are starting to replace their coal plants with renewables. And depending on the energy imbalance market, which deals with the intermittency, right? There's this now pool of utilities on the West Coast that trade energy in 5-minute increments.
Yeah, no, I know that. In fact, I knew the guy who was head of that for California. And he said because you had such a big peak in solar at noon, it was causing him to go nuts because he was burning out transformers at noon. But when he really needed electricity, which was 6 in the evening, then he didn't have the renewable. And so he was forced to import dirty coal derived electricity from Mexico. That's what he told
Yeah.
me.
Yeah. And so that's going to create, but this energy imbalance market, see, the problem with coal is it's so cheap, right? And what you want is an
Well,
energy
solar's getting
imbalance
cheap.
market where the marginal cost of, say, 5 minutes of electricity is high enough that it will provide the incentive for more expensive storage, like batteries and other things. That's less polluting. And California thinks that Mexico's pollution doesn't affect California. Well, no, that's not it's not true. Anyway, it's those wrinkles are being ironed out, and it's going to take another 10 years, but you know, I do
Well, I hope you
believe
do.
I do believe that in 10 years, California will solve its storage problem with batteries and pump storage and other things. And so
Well,
those
there's not
problems
enough mountains for pump storage, and in California, not enough water. But you can do something. And I think the best thing you can do is save your gas because you can make a gas turbine, two-stage gas turbine that uses uses the gas and then the waste heat to run another cycle. And you get 50% efficiency, which is really, really high from a gas turbine. And the important thing about a gas turbine, which is just a jet engine mounted on a pedestal, a concrete pedestal, is you can bring it up and down in milliseconds. You
Yeah.
can, and that makes it really helpful for balancing the load. And that's what engineers do.
Yeah. Another question I have, if no one else does, I hate to seem like I'm dominating, but
Well, you are, but let's just give other people. Anybody else want to say something? I appreciate having you here because it's no embarrassing silence with no questions. Gretchen, you got any questions? Anybody else? Terry, Mac, Ilya, Rob, anybody?
Very interesting. There is an Ollie class that follows this about a half an hour later on EVs, and he's spending a lot of time on battery improvement and recycling of these critical materials.
Well, that's good. And I think we'll figure out a lot of these things. But you have to understand that in the past, we solved an awful lot of problems by throwing more oil at it. And it's going to be more difficult to do that as we go into the future, I think. Now, can we become much more efficient? Can we recycle our copper enough so that we can have this brave new world of electricity driven? I mean, can you imagine all these trucks on Route 5 being driven by electricity? It's pretty hard for me to imagine that. The capital cost of conversion would be enormous for starters. Okay, Carl, you get to ask another question.
You mentioned that natural gas liquids are used to produce gasoline. That's the first I've heard of that. So you're saying propane and butane
Not
can be
propane, but
not
butane.
butane. Butane gets somehow chemically transformed to be a useful liquid in gasoline, but not propane.
I
Okay.
think you can use butane directly.
Okay, interesting.
Just add it to the mix at some ratios the engineers have figured out.
Okay.
No, I was astonished. As I told you, I couldn't figure out how we were burning 20 million barrels of oil a day because we were producing only 13. And it used to be we'd produce as much as we'd burn. But now the oil production has stayed flat or gone down a little bit. But the gas production has gone up so much that we've been able to get a lot of natural gas liquids out of this huge amount of natural gas that we're getting out of the Marcellus Shale and out of Permian in Texas.
Have you studied the fugitive emissions of methane from different forms of gas extraction? Because that's one of those big controversies about whether gas extraction is contributing a lot to global warming. Because methane gas is such a potent greenhouse gas.
Well, it's about 20 times more per molecule, but there are far, far fewer molecules.
Right.
And I think
But
you know that the most important greenhouse gas is water vapor,
right,
which nobody
right.
talks about.
Right.
So I think that I had a friend who would fly airplanes, Cessnas, and he have imaging that could see natural gas. And he was of the opinion that the amount of emissions from pipelines was enormously higher than the official numbers. I don't know.
Well, see,
But
that's a big deal,
in
I think.
yeah, in John Laraire's recent stuff he sent to me, I don't know if I can find this again, but he was saying that I don't know if I can find it, but he was saying that the emissions from natural gas, which used to be very high, are not very high. Here it is. So in one of, see if I, all right, can you see that?
Yeah.
Can you, yeah. So he has in one of these graphs, I think up near the top, the emissions, which are for me surprisingly small.
Huh.
I think we've made a lot of good. I think we're just about to be there. There. So the emissions vented and flared. I guess that's this one here.
Oh. Huh.
And see, it used to be a lot higher, and then they kind of built the pipelines and sold it. And then this looks like with the beginning of fracking, they had they didn't worry about the methane originally, but now they're worrying about it.
Huh. Okay. Interesting.
Well, I find it's fascinating to deal with these things every day. And for me, it's kept my mind young, I guess, and active, and not too much doddering. And I guess we're at the end of our class now.
Can I ask one
So,
more question, Charles, just to follow up to
Yeah,
the one
sure.
about water? You just said that water vapor was the worst, the most, was a greenhouse gas. in
Yes.
it. Yeah, yeah. So how does that relate to my question about water? You said that the water is coming out of the ground. It's not going back into the ground fast enough. It's going into the atmosphere. So that sounds a bit like a bit of a vicious cycle in terms of climate change. Am I misunderstanding this?
No, you're asking very good questions. And I think everybody agrees that as the Earth's atmosphere gets warmer, which I guess it is, that more water vapor, the warmer the atmosphere is, the more water vapor it can hold. And so it's really tricky because high puffy clouds, high cirrus clouds reflect sunlight and cool the earth. But low, regular clouds, I don't know what you call them, they act as a blanket. And I used to show this to my freshmen by getting at one end of the room, and I said I need 5 athletic young men up here. And I got them up there, and I said, now I want you to walk around randomly. And I get at one side, and I was pretty big at that time, 6'2", and played ice hockey and stuff. So I go screaming from one side of the front of the auditorium to the other, and I say, I'm a photon. And I go, and everybody scatter, and I go through. And then I said, now I'm hit the surface of the earth, and I'm transferred into a low energy heat unit. And then I'd go up and try to go through the guys again. And then they'd bump, they would check me and bump me and so forth. So I have much less energy. So the photon has high energy coming from the sun, but the heat wave coming from the earth doesn't have enough energy to punch through the CO2 molecules. And then I'd say, now I'd like 5 athletically oriented girls to come up here. I think we call them girls back then. Young ladies, I hope I said. And so we get 5 guys and 5 girls. And I said, these are the ones that are added from fossil fuel. The CO2 molecules added from fossil fuel. Then I go through the whole thing again, and I'd show how it was harder for me to punch through the CO2 molecules. I keep getting knocked back. And I think they never forgot that, probably, of how the greenhouse effect worked.
Mm.
For those who are worried about the impact of climate change versus depletion, I need a couple more years of data, because we've just had this El Nino, and I want to see what happens when that goes away. But as I've said, I don't fully understand what's going on with greenhouse gases, because the world is something's going on. And you got to realize that methane within 100 years will turn into CO2. And how do you deal with that? Now, do you want to talk some more? Because I got to take a leak.
Yeah,
And-
go ahead, take a leak, then come back.
And if anybody wants to stay here, they can. But what I want to know from you, I don't know if I want to do this course again, because I've done it twice. And, there's some people who like it a whole lot, but an awful lot of people drop out. And I'm not sure that how much people want this. So I would like to have anything you want to say. to me at chall@esf.edu. Should I do this again? Be right back.
I'm gonna take a bathroom break too.
Maybe while you're here, I should ask you this. Anybody have any ideas about how I can teach better? Was this format okay? Am I too noisy, too bossy, too or anything?
I find it excellent.
Oh, thank you. Who's that, Rob?
Yes,
Okay. Thank you, Rob.
this
This
has
is the
raised
Elaine.
this has raised many discussions. I live in a closed island community where we are our own governance in terms of energy and water. And it's generated a number of important conversations in terms of planning.
Okay, good. Any of you, if you have any additional questions, Carl, I was asking whether anybody had any suggestions as to how I could teach this better. And
Wow.
yeah, well, you can write them to me. You say anything you want. You know, I don't mind. I'm a big boy.
Well,
Um,
the only thing I would say is maybe have the class on economic theory earlier, because that is kind of a foundation. Maybe not the first class, because that's the economics theory is a little bit heady. And so, I would, but the rest of the class is, I mean, I'm an economist myself, so I loved the theory part too. But I just think it's a great class. And I think it's a privilege to have somebody who's been doing such fundamental research in these topics to be able to gain your lifetime of knowledge and insight into all of these very important, to me, these are some of the most important issues we've got to deal with in the realm of public policy. And unfortunately, public policy now seems to be mostly about PR than real data and science. But eventually, it's people like you and researchers that in your field that will get called upon when
I'll be dead.
the rubber meets the road. And
I'll be dead.
yeah.
Oh, that's why we got these lectures on tape, I guess. Eric's my archivist, so he's the most important.
Charles, I also appreciate a person of your stature being available to Ollie. I'm very impressed. I'm kind of an energy nerd, and my profession was with the California Energy Commission, and I am in awe of your work, and I really appreciate that you were able to
You embarrass me.
to be here, you know, in Ashland and teaching an Ollie class.
How come there's not 100 people in this class?
Say that again?
How come there's not 100 people in this class?
Yeah, right.
No, they're not all energy nerds like we are.
Yeah.
Or economists or whatever.
I agree. I think
It's
brilliant.
esoteric.
It's so interesting to me.
I mean, you mentioned,
Should I give it in half the time and twice a week?
oh, No, that would be
A long
harder, I
time in
think.
between lectures.
No, I think that's once a week. I think this is a great amount of material and the amount of time you're presenting it. But I think you've got to realize, even with Ashland, and there's so many highly educated people in Ashland, right?
Yeah, but
And
not in science.
right. And so you mentioned you were at a party recently, and
That's correct.
people my guess is when you go to a party, a lot of the people you talk to are pretty well educated people, and they subscribe to the New York Times and to the,
They don't have a
Bloomberg,
clue.
and they don't have a clue about some of the most basic things. And that's partly because, a lot of people don't follow this stuff. They follow all the details of Kim Kardashian's latest facelift
Yeah.
and the latest and greatest on the Trump trial. But there are
I was,
very few energy nerds out there. And I have to say I'm a lot like Elaine in that way. I'm kind of an energy
yeah.
nerd.
Wow, it's
Uh,
great to have you in my class. I'm honored.
I
I'm
think that,
embarrassed,
the,
but
the news you present to us is not real positive. We may face depletion in our children, our grandchildren's time. And, the news media don't necessarily want to cover that kind of thing. So and plus a lot of people just don't understand science and don't want to. So we're up
do
against
you
quite a,
guys watch PBS?
Could you go way further away?
Oh, me?
No, 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 sorry, Charles. I was trying to clear my airwaves here. The point that a lot of this news is fairly negative. Reminds me, I was a product developer for the Nature Company, and one of the product lines that I worked on was about endangered species. And it was very difficult to find ways to present information while selling a product, present the information on the hang tag, which is what we were interested in, that would give information about the endangered species that this product line was representing. And it was a continual challenge. And I think you're up against the same thing, the selling of information that could be overwhelming to any individual who might or might not sign up for the class.
Well, look, I'm going to be on. I'm sorry, you done, Terry?
Yeah.
Yeah, I'm going to be on PBS this fall on an energy series,
Oh, cool.
and so I'll try to send out a message to everybody.
That would be great.
Thank you. Yeah, that would be
And
great.
they said they interviewed 30 people. I kind of blew their socks off. So we'll see.
I consider you a national treasure.
Terry, was that you?
Yes.
Can I tell my wife?
Yes. You can tell anybody you want.
Last I knew, she did not.
Charles, my suggestion about the course, maybe in terms of generating more attendance, might be to think about the title. I think if you were talking about depletion versus climate change in the title, you might find people of greater interest than energy and economics, which sounds much drier.
One thing you all could do is just send, thank you. And I think I agree. One thing you all might do is, if you want, is just send a few sentences to Ollie saying that you think this is really important and that you think that everybody in Oregon should listen to this or whatever you want to say. And how should we deal with it? Because this course was just about 15 people on a good day, and I'm in the good. This is a good class, and I like small classes. Don't get me wrong, but I still think I don't know. Maybe we'll get more attention from the PBS stuff, but people don't even watch PBS. They watch trash TV. So,
There's only so much you
Uh,
can do to help people help themselves.
yeah. Do any of you run into me anywhere in your day-to-day life? At shopping cart or anything? No? If you do, just say hi.
I will. Yes, absolutely. Well, yeah.
Yep,
You
absolutely.
know,
See your wife,
in
and I
ter-
see what your wife in some other classes.
Yeah. She's running for a position on the governing board, and one thing she wants to do is she has pretty good background in science, and as you know, as I tell her, well, you're smarter than me, but I had a better teacher. I said I had Howard Odom, and you only had me. So anyway, she's running for a position on Ollie Council or whatever it is.
well, then
So if you want to,
you'll have a lot of political pull for getting your class to continue.
well, is that what we should do? Should we somehow? I mean, it would be better if it came from if. Do you know each other at all? You all?
No, I don't know any of
It'd
the
be
other
better if,
students.
you know, 3 or 4 of you got together and, you know, beat the drum together at Ollie.
Yeah, I'd be happy to
Um,
do that. I'm only allowed to be in Ashton 6 months a year because I'm a Canadian, so.
Oh,
But I will look for you when I'm there.
oh, oh, are you in Canada right now?
Yeah, I'm in Canada in the summer and I'm living on an island as I was describing. But the other
Oh, we
six
went
months
through all that. Okay,
I'm
yeah,
living in
yeah.
Ashton. My wife is in Ashton taking care of her 99-year-old mother.
Oh,
Oh, wow.
Oh,
well, Rob, what's your email?
I can reply to one of yours, but it's rob@horizonmotionpictures.com.
Well, no, I want to get it to Carl and to Elaine and Eric, I suppose, and Terry.
Oh, I see.
unfortunately, you won't be running into me because I made the mistake of settling in California. I have relatives in Ashland, but I don't with COVID.
Yeah, well, it doesn't
I
matter
haven't
if
been
you if
visiting.
you're taking the course from California. That's great.
Oh yes,
If someone take it from most of it from Italy.
see you have statewide coverage and international participation. I also used to do kind of marketing stuff.
You got an international background?
Inadvertently.
Yeah. Well, I can tell you that the Europeans take energy a lot more seriously than Americans
And
because
yes.
they're getting squeezed in lots of different ways. Look at this. Wait, let me show you the prices of energy. I meant to show this in the bloody talk and I forgot. Just a minute. So you lucky folks will get this. These are all mathematical procedures. I'm just totally into them. You know, this is for all shale things one at a time, and they're all peaking like this. Utica, look at that, perfect Hubbard curve. All right, so hang on. No, I don't. It must be down here. Wait a minute. Ah, here. Here's prices of gas, natural gas. In the US, the purple. In Europe, the blue. See, that's the invasion, the Russian invasion. I mean, we pay a quarter of the price of anybody else. So why is our economy doing well?
Did you say that was natural gas or gasoline?
Natural gas.
Okay, thanks.
Might have gasoline here. Wait a minute. Here's oil. Oh, no, that's natural gas. I'll tell you, this stuff is really interesting. Here's all of our major natural gas plays. You see, they're all, except maybe this blue one, Woodford, they're all peaking. You know, what's this gonna mean? It's gonna be a very, very bumpy ride, I think. And as I said, prices of everything will go up, and people will blame leaders, and countries will become increasingly
You know,
difficult to.
the Russian invasion of Ukraine has been extremely profitable for the United States because we are now the supplier of half the LNG that Europe is importing, and that's where a lot of their gas is coming from now is LNG. We give them half, and Qatar supplies them half. And
And I want to keep it
LNG
in the
is
ground.
extremely expensive.
I want
And
to
yet
keep it in the
we're,
ground.
you know, you almost have to wonder, Donald Trump was saying in the middle of his administration, complaining about Germany's reliance on cheap Russian gas. Hey, you ought to be buying our LNG. And not realizing how expensive LNG was. I mean, even our leaders,
No,
even our
deplete
leaders are
America
not
first.
very bright.
That's how you make America great. Deplete America first.
Yeah, well, yeah. But it's like, are you familiar with Chipola's 5 laws of stupidity? He's an Italian philosopher, and he actually
Yeah.
analyzed stupidity, and he came to the conclusion, and this was like in the 60s. He came to the conclusion that one of his laws is stupidity is much more common than most people think. And I think it's much more common as you get higher and higher in organizations, particularly in political organizations, because, well, for a variety of reasons. But I think stupidity is correlated with desire for power. That's one of Carl's corollaries of Chipola's 5
Well,
laws of
if you want to
stability.
send me that'll be good. Well, I think I'm going to end. It's fun. You can send me an email. You all have my email. You all have my email, right? Send them in. So you can send me a question anytime you want. You can come visit me in Old Mill Way, middle of 5 houses there if you want. Or you can invite myself and my wife to dinner, or you can do anything you want. It doesn't necessarily have to end here. Okay?
Well, thank you, Charles. It's been great. I'm going to use this, by the way, some of this in my class on digging deeper into foreign policy, because a lot of foreign policy is driven by oil geopolitics.
Or it
And
should be called.
yeah, and I think a lot of
Let's see,
the
Carl, did I send you the thing? Did I send you the thing from no, I'm gonna do that. Just a minute. Let me stop sharing.